Hello everyone, I welcome you all in this lecture. So in this lecture we will continue from the previous lecture. So in the last lecture I have explained to you about the aircraft lateral dynamic stability. We have found out the uh, damping derivative due to roll rate, and we have tried to correlate what the CMQ which we have found out in a longitudinal case. So in this lecture we will cover the aircraft lateral and directional mode. So why I am saying aircraft lateral and directional, because lateral directional are coupled. However, for a directional case I will take a separate lectures. Okay. So like in longitudinal case we have seen the short period mode and forward mode, and we have done the detailed analysis on those modes. Like short period mode is a fast damp, and forward mode is a slow lightly damped motion, and we have seen that the craft can attain both short period mode and forward mode depending upon the trim conditions. Like if you are flying very high L by D, it is likely to have a forward mode excitation. Okay, so generally how we as an engineer we do these things, like seeing the aircraft mode and all, figuring out how the aircraft will behave using the mathematics, right? So what we did in the longitudinal case, we linearize, right, in order to see how the modes look like, I mean to say. So in this case also what we will do, we will take the lateral um, aircraft dynamics and we'll try to linearize, and we'll see the reduced order model, which will be having pure roll mode and then dash roll mode. That means uh, dash roll is a coupling motion between the yang and roll. You will see the both the motion together, and then last one is a spiral mode, and we will see uh, whether you can make a complete aircraft inherently stable or not. I mean to say, it is really the case where you can actually design the complete aircraft as a inherently statically stable. Okay, and then the same model we will consider here. This is a motor glider. Okay, so in a lateral case we will be having a 5 state variable: sideward velocity v, roll rate p, yaw rate r, roll angle phi, and heading angle psi. And we will be having two input, delta a as a aileron and delta r as a rudder. So if we want to find out the system matrix A, we have to take a Jacobian. So using the Jacobian, actually we can find out the A matrix. So you can consider, you can take a first row V dot, differentiate with all the state variables. Similarly, second row P dot, differentiate with all state variable. Like that, the last state variable is psi, so you can differentiate psi with respect to all the state variable V, P, R, phi, and psi, and then you will be having a matrix. Similarly, if you differentiate V dot, P dot, R dot, phi dot, psi dot with respect to the delta A aileron input and delta R rudder input, you will get the control matrix B. Okay. So once you substitute the trim condition value, you will get the modes. I mean to say, and then the question comes, what will be the trim condition? So as we have taken the last trim condition, I mean to say in the longitudinal case, we have taken the altitude of 8,000 feet and trim speed is 45 meter per second. This is design speed. And if you find and all other parameters are available for this aircraft, you can go to internet and you can take the parameter. And if you don't get, I mean to say, you can actually ask me. I will provide you the data separately, like mass, inertia, wingspan, area, chord, etc. Okay, if you want I can provide the aerodynamic model also, which I have estimated analytically. Okay, now once you have a system matrix, and then how will you find out the root? Using lambda I minus a determinant equal to 0, then you will find out the 4 root on this trim condition. What is trim condition? 8,000 feet, 45 meter per second is the design speed. So you will end with three mode here. One is roll mode, and 4 root is there, but mode is 3 because dash roll mode is coupled having 2 roots, okay, pair. So one is roll, that is called pure roll mode, okay, and another one is a dash roll mode, and the last one is a spiral mode. So pure roll mode, that means that depends the pure rolling motion. For example, if the aircraft is banged in this way, immediately it will back, or it will take some time to get the original position. So with time it is coming back, okay, that is a pure roll motion, okay. That means it is coming back to the original position with the time. That means what is happening, there is no oscillation is involved. So that means the damping ratio zeta is 1 and root lies on the right half of the plane, and if the root is more far from the origin, that means you have a very fast damping, okay. For example, in this case we are getting approximately -12. So if it is -15, you will be having more damping, and if it is -1, you will have a little less damping. So this way you can have a feel for that key based on a location of a, what you can see here, pole. You can actually have a feel that key whether the system is more dynamically stable or not, okay. Now when you have a very fast damping, that means obviously you will take less time to get back to the original position. That means time to half will be less. So here in this case 0.059 and 0.06, less than a second it is coming back. And I already told you about time to half, time to double, number of cycle to half and double, okay. So that means time to half refers to the dynamically stable system. That means amplitude, let's say first is x naught, and if it is reaching to the x naught by 2, so how much time it is taking, that is called time to half. So from x naught to x naught by 2 it is going, so obviously the system is dynamically stable because amplitude is reducing. So it is a when the system is dynamically stable, so time to half will come. Similarly, when there is a dynamically unstable system, so the amplitude will increase. So let's say from the x naught it will become, let's say, x 2x naught. So how much time it will take to become 2x naught, that will time referred to as a time to double, okay. And based on the sign of a pole, you can actually say that key whether my system is stable or unstable. For example, if the real part is negative, that means obviously we have a stable system because e to the power minus lambda t will have a convergence motion, okay. All right, so you can see that the roll mode is pure negative. We don't have any kind of imaginary part here, only pure real part. So that means you will see you will not see any kind of oscillation, only convergence because of negative part. And in a dash roll mode, where you will see there is a motion between yaw and roll. So if you neglect the rolling motion and consider the side slip and yaw, you will have a dash roll mode, okay. Put the conditions and then you will get the dash roll mode. So here you can see that the dash roll mode is minus 0.537 plus minus I 2.095, okay. The frequency is 2.1 and zeta is 0.248. So that is, it is also some kind of lightly damped, not like a forward. It has a more frequency damping ratio than forward, but it is considered to be a lightly damped mode. So we should avoid hitting this kind of mode in flight, okay. And if this mode is hit somehow, then we have to immediately counter this using the control inputs, okay. So you can see you have a both real part as well as imaginary part in dash roll case. So that means real part is negative, obviously is a stable case, okay. But the imaginary part you have, that means there is some kind of oscillation. So that is why in this lateral and directional case, you will see only dash roll will have some kind of oscillation because of imaginary part is present, okay. Now the in this case the time to half is 1.29. That means what the case we are getting like pure roll mode, it's very fast. Then compared to the dash roll mode, it is taking more time, okay, more than a second, okay. And if you compare with the 0.059 case in pure roll mode, you are taking more time here in the dash roll mode, okay. Now the last one is a spiral mode, okay. So spiral mode, let's say It occurs generally when you fly very low angle of attack and with high bank angle, and you will take a turn. Okay, so in this case you will lose the altitude also. So like for example, I have done the spiral recovery for a F-18 aircraft. So I found that the altitude loss is about 1.28 meter per second. In this mode you will lose the altitude with the time. Okay, and it is unstable also. For example, let's say a pure roll mode, dash roll mode is stable. Okay, but spiral mode has a positive real part. It lies on the right half of the plane. So that means with the time it will converge. Okay, and it is close to the origin here in this case. So the time to double will come to the picture. And now, and how I have, you can estimate the time to double and time to half. You can go back to my longitudinal aircraft dynamic stability lectures. You will find out. Okay, no problem. Now time to double is 22.3. So that means after 22 seconds the amplitude will double. So as a pilot or as an engineer, you can think if the time to double is more, it is good to have a time to double more, because pilot will have a sufficient time to recover the aircraft. It's, if let's say time to double is just a 1 second, so just after when you hit the spiral mode, after 1 second, time to amplitude will become double, and then more and more with the time as time progress. So that means if you are having more time to double, it is good for us, because we will be having a sufficient time to recover the aircraft. Okay, so how can you get this mode? By setting roll rate equal to 0 and rudder deflection equal to 0. However, more mathematically and physics wise we will discuss in the future also, because when we will cover the aircraft directional dynamic stability, then again we will see this kind of slides, and again we will try to give you more feeling, because that time we will estimate the uh, damping derivative in a yaw case and more other derivatives. Then we will see together as a lateral and directional motion, and we'll try to have a more feel. Okay, okay, so you can see the root location I have plotted in root locus. You can see on a figure A I have given placed the roll mode, and in figure B you can see the pair of the mode which is a dash roll, and one is a spiral mode which is lying on the right half of the plane. And the when you completely do the transfer function and all, you will see the zeros also. So please here focus on the poles which is cross marked here. Okay, okay, so in the upcoming classes we will discuss the aircraft uh, directional stability, dynamic stability, directional control, and then we will try to combine the, we'll look the directional motion and lateral motion together, and we will try to have a more feel for this kind of motions. Okay, we'll meet in the next class. Thank you so much for attending this lecture.